right now, I mean, if you step outside, your AC condenser's probably screaming, right? Pulling in like, what, 105-degree ambient air, trying to compress refrigerant against this massive thermal gradient?
Oh, yeah, it's just burning through electricity.
Exactly, just to cool the air above ground. But the crazy thing is, just like 6 to 10 feet beneath the grass in your backyard, the Earth is just sitting there at a perfectly stable, totally unbothered 62 degrees.
It's completely indifferent. I mean, it ignores the blizzards in January. It ignores the heat waves in August.
Right.
It essentially acts as nature's infinite thermal battery. Because, the mechanical effort required to move heat into or out of a stable 62-degree medium is just drastically lower than wrestling with those crazy atmospheric swings.
Which makes sense.
Yeah, and that physical reality is really the entire basis of geothermal efficiency. But, and this is the big but, tapping into that subterranean battery requires a really deep understanding of the geology that you're actually building on.
Which brings us perfectly to our mission for this deep dive. Today, we are pulling from the field notes, the technical specs, and the training manuals of Dave Hartzell.
Yeah, an absolute wealth of knowledge there.
Truly. He's an IGS HPA accredited geothermal veteran. He's got like 45 years of experience designing these exact systems, specifically based out of Kingfisher, Oklahoma.
Right, which has very specific ground conditions.
Right. So we are looking at central Oklahoma's unique geology to decode the two vastly different philosophies of geothermal heat transfer, which are the closed loop and the open loop.
They dig too.
Yeah. We're going to break down how the thermal exchange physically works, analyze the actual 2026 installation costs, and basically arm you with the ultimate cheat sheet to avoid, catastrophic and highly expensive failures on your own property.
Because, treating a geothermal installation like it's just a standard appliance swap, like changing a fridge, is a massive miscalculation.
Oh, for sure.
The land dictates the rules. And if you try to force a system that fights the local geology, well, the land is always going to win.
Okay, let's unpack this. We need to look at the two distinct paths engineers actually use to get that 62-degree temperature out of the dirt and into your living room. So let's start with the closed-loop philosophy. Looking at Hartzell's specs, this is essentially, a 50-year sealed circuit?
Correct. Yeah, the closed loop relies on high-density HDPE pipe buried in the ground.
Right.
And what makes this system unique is that the fluid inside, which is usually the specific mixture of water and an antifreeze like propylene glycol or methanol, it never actually touches the earth.
Like ever?
Right, never. It is a completely sealed loop. The pump just circulates that exact same batch of fluid continuously for decades.
Wow.
So the fluid absorbs that 62-degree baseline temperature right through the wall of the plastic pipe, carries it into the heat pump in your house, exchanges the thermal energy, and then just cycles right back underground.
Okay, got it. And the way you bury that HDPE pipe, that kind of comes in 3 different flavors, right? Depending on your acreage. You've got the horizontal loop, where contractors dig trenches about 6 feet deep, running 300 to 500-foot circuits.
Right, if you have the space for it.
Yeah. And then there's the vertical loop, which seems like a much heavier footprint operation. That requires a full drilling rig to bore straight down 200 to 400 feet.
Yeah, usually dropping 4 to 6 individual boreholes for a standard-size home.
Man. And then finally, if you happen to have a large, deep body of water on the property, you can just sink coils of pipe directly into it for a pond loop.
Yeah, and the underlying physics for all 3 of those are identical, really. It's just conduction through a sealed barrier.
Makes sense.
And in the case of vertical boreholes, it's not just, dropping a pipe in a hole. That's a common misconception.
Oh, really?
Yeah, drillers have to pump a specialized thermal grout. It's often this mix of bentonite clay and silica sand. They pump it all the way from the bottom of that 300-foot hole back up to the surface.
Oh, wow, so it's completely filled.
Exactly. That grout encapsulates the pipe, displacing any kind of insulating air voids, and it basically creates a direct, highly conductive bridge between the pipe and the surrounding bedrock.
Oh, okay, so that brings us to the second philosophy, which is the open loop. And this is, an entirely different mechanical approach.
Very different.
Instead of circulating that same sealed batch of antifreeze, an open loop just pulls continuous fresh groundwater directly from an existing water well.
Yeah.
It moves, about 10 to 15 gallons per minute, runs that 65 to 70 degree well water through the heat exchanger exactly once, and then immediately discharges.
Right out of the system, yeah. So it relies on advection rather than pure conduction.
Okay.
Because you are constantly introducing this massive volume of new water that is already at your target temperature, the heat transfer is just incredibly rapid.
Right, it's constantly refreshed.
Exactly. You extract or reject the heat you need instantly. Therefore, an open loop requires a fraction of the buried piping compared to a closed loop.
Okay, so let me see if I have this right. A closed loop is like a reusable ice pack, right?
Mhm.
So you keep putting it back in the freezer to chill down over and over, relying on time and surface area.
I like that, yeah.
Meanwhile, an open loop is like just drinking straight from a continuously running, super cold garden hose.
That is an excellent way to visualize the difference in thermal mass management, actually.
Thanks. But, okay, if an open loop uses way less buried pipe,
Yeah.
because that move-in water holds all the energy, I have to assume it requires significantly less heavy machinery and digging, right?
Oh, absolutely.
Doesn't that make it the undisputed champion of these two systems? I mean, why wouldn't you just do that?
Well, if we connect this to the bigger picture, less digging absolutely translates directly to the bottom line. The loop installation is the single largest cost variable in geothermal.
Right.
Because the mechanical equipment inside your utility closet, the ductwork, that's all virtually identical regardless of the loop type. You are strictly paying for the method of interacting with the earth.
Yeah, and I was looking at Hartzell's 2026 data for a standard 3-ton system in central Oklahoma, and honestly, the cost delta blew my mind.
It's steep.
Vertical closed loops are peaking between $28,000 and $34,000 for the installation. Which, I get it. You are mobilizing a 30-ton mud rotary drilling rig. You're cutting through sandstone, pumping tons of silica grout. That's a massive job.
It is.
Now, if you have the land for horizontal trenching, the price drops to a $22,000 to $28,000 window. The pond loop sits around $18,000 to $24,000.
Yeah.
And the open loop, assuming you already have the well.
Yeah, that's the key part.
Right. It's coming in at just $14,000 to $19,000.
Yeah.
So you're talking about a $20,000 gap between the vertical and the open systems.
Yeah, the upfront capital required for a vertical closed loop is just a massive barrier for a lot of homeowners. But what's fascinating here is how those really diverse installation costs contrast with the actual operating costs.
Right.
Because once the system is buried and running, the efficiency normalizes across the board.
Yeah, I saw that in the data, and it seems almost counterintuitive. Like, for a 3,000 square foot house in Kingfisher, the operating cost to heat and cool the home for the entire year is roughly $1,200 to $1,500.
Right.
And the difference in your monthly utility bill between that $34,000 vertical loop and the $14,000 bin loop is about $80 for the whole year.
Yeah, the mechanics of the heat pump govern that efficiency, basically. A closed loop is marginally more efficient, which is where that slight $80 edge comes from, because the system designer can optimize the specific gravity of the antifreeze mixture.
Oh, I see.
Yeah, they can manipulate the fluid temperatures. You can chill the closed loop fluid down to like 30 degrees before sending it into the ground, which maximizes the temperature delta for heat rejection in the summer.
Right.
But with an open loop, you are completely locked into whatever the static temperature of the aquifer is, which in central Oklahoma sits slightly warmer anyway, around 65 to 70 degrees.
Okay, wait, I have to push back here. If the yearly operating savings are essentially a rounding error, literally just $80 a year, but the upfront installation saves you up to $20,000, why wouldn't every single person listening to this just sink a well and run an open loop?
It's a fair question.
Like, it seems completely irrational to spend 30 grand on drilling boreholes when the performance is identical.
And that is the exact trap so many property owners fall into. They look at the spreadsheet, they see a $20,000 savings, and they completely ignore the environment.
Okay.
The reason you don't default to an open loop is Mother Nature. Open loops have 3 distinct severe failure modes that can turn that initial $20,000 savings into just a permanent maintenance nightmare.
Oh boy.
Yeah. The first one is water quality.
Right, because you are pulling raw groundwater directly into a highly precision mechanical device. And Oklahoma groundwater is notoriously harsh, right? It's heavy in iron, calcium, and sulfur.
Very harsh.
So how does that actually physically impact the system?
Well, to put it simply, it destroys the heat exchanger. Let's look at calcium first. When hard calcium-rich well water hits the really hot plates of the heat exchanger during the summer cooling cycle, the heat causes those dissolved minerals to precipitate out of the water.
Like hard water stains in a shower.
Exactly, but inside the machine, they form this thick chalky scale directly on the metal, and that scale acts as a thermal insulator.
Oh, so it blocks the heat transfer.
Precisely. Within a few months, it completely blinds the heat transfer, and your system's efficiency just plummets.
Man. And what about the iron and sulfur?
Iron bacteria creates this thick biological slime that rapidly clogs flow filters.
Yeah.
Yeah, it literally strangles the gallon per minute rate the system needs to even survive. Sulfur, meanwhile, causes aggressive galvanic corrosion. It will literally eat through standard copper and brass fittings.
So it just dissolves the plumbing.
Yes. So, to combat this, you have to upgrade the heat pump to a specialized cupronickel or stainless steel heat exchanger.
Which I'm guessing isn't cheap.
Not at all. That immediately adds $800 to $1,500 to your upfront cost. And that's not even mentioning the potential need for continuous chemical pretreatment systems just to keep the water from dissolving your system.
Okay, so poor water chemistry turns your cheap open loop into like a high-maintenance water refinery.
Basically, yeah.
But let's say I pay for the Cabronical upgrade, I bite the bullet, I'm safe now, right?
Absolutely not. Which brings us to the second failure mode,
Mm.
water quantity.
Ah.
This is really the quiet killer of open loops. People assume that because they they just have unlimited water. But a standard 5-minute pump test only measures the static column of water in the casing.
Right.
It tells you absolutely nothing about the aquifer's recharge rate over time.
Because an open loop requires, what, 10 to 15 gallons per minute?
Mhm.
So over a 10-hour cooling cycle in August, you are asking that well to produce up to 9,000 gallons of water in a single day.
Exactly. And during a peak heat wave, that continuous draw creates what's called a massive cone of depression in the aquifer right around the well pump.
Like a sinkhole of water.
Yeah, exactly. And if the surrounding geology cannot recharge the water fast enough to keep up, the dynamic water level drops below the pump intake.
Oh, no.
Yep. The pump sucks air, the water flow stops completely, your heat pump faults out on high head pressure, and your air conditioning shuts down precisely when you need it most.
Okay, that is a disaster scenario.
Yeah.
And even if you have perfect infinite water, you still face the third hurdle, right? Which
Right.
is discharge logistics.
Oh, yeah.
Because you are pulling 9,000 gallons a day, you have to legally put that water somewhere.
You can't just make it vanish.
Right. Depending on your county, you can't just flood a local creek or dump it in your neighbor's pasture. You often have to permit and drill a dedicated return well, which adds thousands of dollars right back into that initial cheap price tag.
Exactly. Which is exactly why the closed loop, despite that massive upfront cost, is often the necessary choice.
Yeah.
By sealing the fluid, you just eliminate water quality scaling, you eliminate aquifer depletion, and you eliminate the discharge permits entirely.
But to be fair, a closed loop isn't completely invincible just because it's sealed. The source material highlights some real physical risks.
Sure.
I mean, HDPC pipe is tough, but it's buried in an active environment.
Mm-hmm.
Soil settlement, invasive tree roots, or, a careless landscaping contractor with a backhoe, they can compromise a 50-year loop in an afternoon.
Happens more often than you'd think.
And if you get a pinhole leak 150 feet down a vertical borehole, you can't just dig it up with a shovel. You have to use specialized sonar or pressure isolation tools to even find the leak, which can cost $3,000 to $8,000 just to locate and bypass that damaged section.
Yeah, physical damage is a risk, yes. But honestly, the far more common sort of invisible risk to a closed loop is thermal saturation,
Okay.
which is entirely dictated by soil science. This is where system sizing becomes absolutely critical, especially in environments like central Oklahoma.
Here's where it gets really interesting to me.
Mhm.
I know the geology in Kingfisher is highly specific. It's a lot of red clay sitting over a sandstone and shale.
Right.
So how does that specific dirt change the efficiency of the pipe buried inside it?
Well, the soil surrounding the pipe acts as your primary heat reservoir. Its ability to absorb or yield heat. So its thermal conductivity relies heavily on moisture.
Okay.
Water bridges the microscopic gaps between the soil particles, allowing heat to travel efficiently. Now, wet red clay conducts heat very, very well. But during a prolonged summer drought, as that clay dries out, the water evaporates and leaves behind tiny air voids.
And air is a terrible conductor of heat. It's essentially an insulator.
Precisely. So as those air voids form, the thermal conductivity of that clay can drop by an astonishing 40%.
Wow.
Yeah. Sandstone maintains fair conductivity year-round, and solid bedrock is excellent. But if your horizontal loop is just sitting in a dry clay layer, its ability to reject heat into the earth is drastically reduced.
Okay, let me try an analogy here to visualize this thermal saturation. It's kind of like trying to mop up a continuous spill with a sponge that is already completely soaked.
Yeah, I like where this is going.
If an installer underestimates your soil's conductivity and they don't bury enough pipe, you're basically asking a very small cubic volume of dirt to absorb an entire house's worth of blazing summer heat.
Right.
And eventually that specific patch of soils just fills up. The temperature of the dirt itself rises from 62 degrees up to maybe 85 degrees. You lose your temperature delta, the heat transfer stalls out, and the indoor AC simply stops cooling because the earth just can't take any more heat.
The system essentially chokes on its own rejected energy. That's a great analogy. And this is exactly why soil typing is the absolute foundation of any closed-loop design.
It has to be.
Right. If you are burying a horizontal loop in dry, sandy soil, which has terrible thermal transfer, you might need to trench 500 linear feet of pipe for every single ton of heating capacity.
Jeez.
But if you have excellent wet clay or solid bedrock, you might only need 350 feet per ton. The soil changes the whole design.
So what does this all mean for you, the listener, especially if you are staring down a contractor quote right now? We've analyzed the $20,000 difference in installation capital, the mechanics of scaling and aquifer depletion, and the very real threat of thermal saturation in dry soil.
It's a lot to weigh.
It really is. So I think it's time to build the master blueprint. Based on Hartzell's 45 years of data, how do you actually match the right loop to your specific piece of land?
Okay, let's walk through the definitive matchmaking scenarios. Scenario 1. You have large rural acreage, say 5 acres or more, but you do not have an existing high-capacity water well.
So the match here is the horizontal closed loop, right? You have the vast physical space required to dig hundreds of feet of trenches, which completely avoids the massive cost of bringing in those vertical drilling rigs.
Exactly.
And because it's closed, you don't have to worry about lacking a good water source.
Spot on. Okay, scenario 2. You have that same big acreage, but you also have a high-yield, proven irrigation well.
In this case, the match is the open loop. It gives you the fastest installation and the absolute lowest upfront price.
Right.
But you must verify the water chemistry and upgrade to a cupron-nickel heat exchanger if necessary. And obviously ensure you have a legal discharge route.
Critical steps. Yeah. Scenario 3. You live on an in-town lot, or like a standard suburban subdivision that's under half an acre.
Then the match is the vertical closed loop.
Yeah.
You simply do not have the physical square footage for horizontal trenches.
Whoop.
Vertical boreholes only require about 15 to 20 feet of spacing between holes, making them really the only practical option for a small footprint. You just, have to brace for the higher end of the pricing spectrum due to the drilling.
Yeah, you pay for the lack of space. And finally, scenario 4. Your property features a pond that is at least a quarter acre in size and consistently maintains a depth of 8 feet or more.
The match is the pond loop. This is often the ultimate cheat code for balancing price and reliability.
But wait, why is the 8-foot depth the absolute non-negotiable metric here? Because at 8 feet you get below the pond's thermocline.
What?
Thermocline. That is the transition layer where water temperature drops rapidly. The surface of the pond might be 90 degrees in late August, but down below 8 feet, the water stays cool, dense, and thermally stable.
Oh, I see.
Yeah, it provides a perfect, highly conductive medium for heat exchange, entirely without the cost of drilling through rock. But if the pond is too shallow, the entire water column heats up in the summer or freezes solid in the winter, and that destroys your thermal delta.
Wow, okay, so that is the cheat sheet for the land. But we also have to talk about protecting yourself from an installer who doesn't respect the geology. Like, what are Hartzell's rules for hiring a contractor so you don't end up with a thermally saturated failing system in 2 years?
The single most critical rule is demanding site-specific load-matching calculations in writing. Never, ever accept guesses or rules of thumb.
Good advice.
If a contractor is proposing an open loop, you demand a 1-hour continuous pull test on your well. A 5-minute flow test is totally useless for predicting an August heat wave capacity.
Right.
And if you are doing a closed loop, require the contractor to verify the proposed bore depths against the manual J heat load calculations, specifically modeled for your house's insulation and square footage.
So basically, if a contractor gives you a flat per ton price over the phone, without asking to evaluate your soil type or testing your well capacity, they are selling you a price tag, not a functional system.
Exactly. Run away.
And it's also worth noting that reputable installers view these systems as long-term infrastructure. They offer maintenance plans, typically ranging from like $360 to $499 a year.
Yeah, highly recommend those.
Right, because those top-tier plans include vital services like loop repressurization. Since HDPE pipe slightly expands over time, the fluid pressure drops, and maintaining that pressure is critical for flow dynamics. So it is a long-term relationship, not a drop-and-go transaction.
A geothermal system is deeply physically integrated into the hydrology and geology of your property. It requires a steward who actually understands those forces.
Bringing it all together, I mean, the geothermal technology is profoundly elegant. It leverages the beautifully stable temperature locked beneath our feet to completely bypass the chaos of atmospheric weather.
It really is elegant.
But selecting the shiny metal box in your utility closet is only half the equation. Whether you choose the sealed 50-year reliability of a closed loop or the high-flow advection of an open loop, you don't get to just pick your favorite off a menu. The land always has the final say.
It does. But, if we connect this to the bigger picture, it leaves us with a rather provocative thought about the future of residential infrastructure.
Oh.
Yeah, we noted earlier that the biggest hurdle for suburban homeowners is the massive $30,000 plus upfront cost of mobilizing drilling rigs for vertical boreholes on small lots.
Right, it's a huge barrier.
But what if we stopped thinking of geothermal as a private individual luxury? Imagine if future subdivisions drilled a massive communal grid of deep vertical boreholes before the houses were even built.
Oh, wow.
Right? Every home could simply plug their individual heat pump into a shared neighborhood loop, treating the Earth's stable 62-degree temperature exactly like a public utility water line.
Man, that would completely eliminate the individual upfront cost barrier, spreading the infrastructure cost across the entire development.
Exactly.
It's a brilliant way to democratize the efficiency. So the next time you are sitting in your living room, listening to that condenser outside screaming against a 105-degree day, or watching your natural gas bill skyrocket when it's 10 degrees out, just look out at your backyard. The solution to perfect comfort isn't about fighting the sky. It's already there, sitting quietly in the dirt 6 feet down. You just have to know how to tap into it.